All right, question 6 says find the work done by the force field in moving an object from P to Q. And for part A, we have the field F, which is e to the minus yi minus x e to the minus yj. And we're going to move an object from the point P with coordinates 0, 1 to the point Q with coordinates 2, 0. And notice the problem does not specify a path from P to Q, which suggests that the line integral that we'll use to compute the work is independent of path. And from the last video, that then would imply that this vector field F is conservative. So we'll start by finding a potential function, phi, and we can do that in much the same way we've done a couple other problems so far up to this point. So we got the following, right? I'm going to call the I component of f p, and if f is going to be conservative, right, then it's equal to the gradient of some potential function phi. So p will equal the x derivative then of phi, just equating I components. Likewise here for q. And so the fact that the x derivative of phi then is equal to p, which is just e to the minus y, then tells us, if I integrate with respect to x, that phi of xy will be x e to the negative y plus some function I'll call c that depends only on y, right? So it's constant with respect to x. Okay, so now our job is to find this function c of y, and to do that, let's go ahead and differentiate this right here with respect to y. So that's going to give us that the y derivative of phi is minus x e to the minus y plus the derivative of c with respect to y. And since the y derivative of phi has to equal q, and we know that q is minus x e to the minus y, this expression then is equal to minus x e to the minus y. And since I have that expression on both sides here, that says that c prime of y then is 0. And so c of y must just equal a constant. I'll call it a. And so we now have our potential function phi, right? It's x e to the negative y plus c of y, which we just found was this constant a. All right, so then the work done in moving this object from P to Q can now just be found by evaluating this potential function at these two endpoints as subtracting, and so we get a value of 2 there for the work done by the field. Cool. All right, so now part B is really similar. The main difference here is that this is a three-dimensional vector field. Okay, so we'll go ahead and start by finding a potential function phi, which will be a little bit messier, but it's really the same idea. So I'm going to label p here, which is the I component of f, as partial phi partial x, and likewise for q and r. So if I start from the fact that the x derivative of phi is p, which is 2xy minus z squared, then I can integrate with respect to x to get that my potential function phi, which now is a function of three variables, is going to equal, well, the integral here with respect to x, which would be x squared y, minus the integral of this with respect to x, that'd be minus xz squared. And now this is a bit different, right? Since we're working with a function now of three variables, when I integrate with respect to x, I'm holding both y and z constant. So I'm going to write this as c1 of y and z. So this is a function that depends only on y and z. And so now we need to go ahead and find this function. So next, we'll go ahead and differentiate phi with respect to y. So from right here, we're going to get x squared. The derivative of this part will be 0. And see, if I differentiate this with respect to y, since it's a function of two variables, this really is a partial derivative now with respect to y. So I have that the y derivative of phi is equal to this expression, but I also know that the y derivative of phi is equal to our function q, which is just the I component of the field f. So I go ahead and equate that with q, which is x squared plus 2z. Notice I have an x squared on both sides, so that tells us that the partial derivative of this function c1 with respect to y is then equal to 2z. All right. So then what can I do to find C1 from here? Well, notice if I integrate with respect to y here, that's going to give us that C1 is equal to 2yz plus, well, some other function I'm going to call C2, and it depends only on z. Okay, so I'm getting closer, right? So now I know that C1 is 2yz plus some expression here that depends only on z. So how do I finish and find this expression C2? Well, let's go ahead, go back to this potential function equation right here and differentiate with respect to z. So that's going to give us a 0 here, a minus 2xz from this middle term, and then here I'm going to get the partial derivative of c1 with respect to z, right? But now I know that c1 is equal to this thing, so if I take the partial derivative of c1 with respect to z, that's going to give us 2y plus c2 prime of z, where this derivative's taken with respect to z, and I still have my minus 2xz out in front. And then lastly, since we know that the z derivative of phi is equal to this k component for our vector field f, so in other words, it's equal to this function r, which is 2y minus 2xz, equating all of that and noticing that I have both the 2y and the minus 2xz on both sides, that implies that c2 prime of z is 0, and so c2 then is just a constant. So putting that all together now, okay, we have that phi, our potential function, is x squared y minus xz squared plus c1, which I know is what? It's 2yz plus C2, which we found down here is just a constant. Okay, so to compute the work, right, just to finish things off, we can now go ahead and just evaluate this potential function at the endpoints and subtract. And when you do that, you wind up getting a value of 16, which is all quite nice, right? The other comment I want to make here, though, is that this is a very systematic way to go about finding this potential function. But it is pretty tedious and it's easy to get a little lost in some of these details. Okay, another option here, especially for a vector field whose component functions are not terribly complicated, you might be able to just guess, okay, using the fact that these are just all polynomial functions. Um, you're just looking for a function whose x derivative is this expression, whose y derivative is this, and whose z derivative is this. So if you play around a little bit, you might be able to arrive at this potential function a little bit faster than this systematic approach. But nonetheless, this is quite nice. I mean, it will always do the job for you. It's just it is easy to get a little bit lost. So keep that in mind. All right, well, that's going to do it for this question. I'll see you in the next video. Thanks.